A mass is attached to an unstretched spring. This position is the unstretched natural position of this spring. A mass whose is connected to that spring. No stretching, no compression. That's why this mass stays in its place. But if you pull this mass to the right by applying some force, of course, as you apply the force, spring will be stretched. Yani this hand, my hand, is pulling this mass with some force, blue applied force, because I am applying this force. And because I applied this force, spring will be stretched. This is the unstretched position. This is the new position. So stretching is X. This spring is stretched by a distance X. And also this mass displaced the same distance X. Yani mass position has changed. It was initially in here, but now in here. So displacement of the mass and amount of stretching of the springs are equal. But if F applied increases, which means if I apply more and more force, so I know that X increases proportionally. So applied force and F applied force by my hand and stretching are proportional. And from this proportionality, I get an equation, which is K times X. F applied is equal to K times X. However, when I was holding this object at this position, assume that I pulled them and now keeping it at rest. If an object mean net force acting on this object must be equal to 0. But now in the diagram you only see one force F applied. So for to be at rest, we need net force to be 0, which means there must be an oppositely directed force acting on the mass. This force is because of the spring. Spring will be pulling this object back in negative X direction to the left. Yani as F applied stretches the spring, spring pulls the mass back by exerting an oppositely directed force named as elastic force or spring force. Why is it called elastic? Because spring is an elastic object. Elastic object is the object in the 10th grade you defined. After deforming an object, after changing the shape of an object, if object takes its original shape, that object is called elastic object. Because when you release this object, when you remove your hand, you are going to see that this spring takes its original shape. That's why spring is an elastic object. Name of this force applied by the spring is called elastic force or spring force. This red one, this red force. There are two forces acting on this object right now. One of them is because I am pulling to the right with my hand, applied force. Second one is elastic force. The spring is pulling the object back to its unstretched position. This is unstretched position. So as you see this red arrow, if elastic is pointing towards this unstretched position. This elastic force, or other name is spring force, is always in the opposite direction of the mass displacement. So displacement of the mass, look at the direction. It is to the right. Look at the direction of the restoring force. It is to the left, always in the opposite directions they are. Yani if the X is to the right, restoring force upon elastic force will be to the left. One property is that their directions are opposite. But second thing is, it is directly proportional to displacement of the mass. Yani when you stretch it more and more, this elastic force also increases proportionally. It's in magnitude. So it's directly proportional to displacement of the mass. Yani F elastic, this elastic force, is proportional to X. But in the opposite direction of X. Proportional, but opposite in direction. So then, equation for this elastic force is going to be negative Kx. This negative is indicating that this force is in the opposite direction of the mass displacement. This negative is coming from that. This equation is known as Hooke's law because the first scientist who discovered this relation between X and F elastic is Robert Hooke. He found that the most mass spring system obeys this simple relationship between elastic force and displacement. Yeah, if you stretch the spring to the right, elastic force becomes to the left in the opposite direction. But if you stretch it more and more, elastic force also increases proportionally. This equation is telling you these two things. One of them is elastic force in the opposite direction of the displacement or in the opposite direction of the stretching. Second thing, elastic force is directly proportional to displacement of the mass. And this force always pushes or pulls the mass back towards its original unstretched position. Look at direction. Look at direction in here. So when I stretch it to the right, this force is pulling the object back to the left. Why? Because this is unstretched position. Its direction is always towards the unstretched position. But if you push it, now in here I pulling the mass. If I push the mass, now I pushed it. Now the displacement direction is to the left. Now restoring force will be to the right now. So they are always, these two vectors will be always opposite in direction. Again, towards the equilibrium position. This is unstretched position. Unstretched position. Yeah, the direction of elastic force, direction of this spring force will be always towards unstretched position. That is why this force is given a common name. This elastic force or this spring force is given a common name. This name is restoring force. Restore. Restore means as a word to bring its original shape. For example, if there are some historical buildings, if there is some damage, so you are taking this building, making something, and then you are restoring it to its original shape. This force is also doing the same thing. So when object is displacing away from the equilibrium position by your hand, this force wants to take this object back to its original unstretched position. That's why its name is restoring force. If they ask you, they can, what is the restoring force for mass spring system? Your answer will be it is elastic force, or another name, spring force. Any questions about this slide?
Teacher?
Yeah.
Is restoring force's magnitude equal to the applied force's magnitude?
Yes, equal in magnitude, because if you are keeping it at rest, which means they must be equal in magnitude, is it?
Yes, that's right. It's like a counteracting force to the applied one.
Yes. Then now I will define what does this restoring force does. Why is it so important? Now this is the case. As I said, of course, to stretch a spring, you have to apply some force. Yani if you don't pull it, you cannot displace the object. First, you have to pull the object from this unstretched position. You should stretch to the right or compress to the left. You should do one of them. Yani object must displace initially. So now I am keeping this object at rest in my hand. That's why V is equal to 0. And I know that elastic force is always towards the equilibrium position, this unstretched position. My force is away from the unstretched position. As soon as the applied force is removed, if I release this object, this applied force is removed. Only one force will act on this object, which is the elastic force. This elastic force will start this object vibrating back and forth around this unstretched position. This elastic force, this restoring force will cause this mass to vibrate back and forth around this unstretched position. So reason of this vibration is reason of this oscillation is the restoring force acting on the object, which is the elastic force, only force. So then if a spring is stretched by applying some force on the object, then the mass is released, because to start the vibration, I have to do that. Otherwise, object cannot start vibrating. First, you should give some energy by applying some force, applied force. But after that, you are going to release it, just like this one. When you release it, due to this restoring force, the mass starts vibrating back and forth. Mass starts vibrating back and forth. Vibrating back and forth is called what? Periodic motion. So this motion is a periodic motion. It's vibrating back and forth. But this periodic motion, this vibration is due to a restoring force. This is key. If a restoring force causes a periodic motion, if a restoring force causes a periodic motion, that periodic motion is named as simple harmonic motion. Yani, this is definition in the book. Any periodic motion, yes, simple harmonic motion is a periodic motion. But what kind of periodic motion? That is the result of a restoring force. Yani, if there is no restoring force, there is no elastic force, if it is not a spring, this oscillation, this vibration could not be possible. So it is possible only because spring is an elastic object, only because there is an elastic force acting on this object, and this elastic force always pulls object back to equilibrium or unstretched position. This is definition of simple harmonic motion, and I think this is the important, very important definition to differentiate between the periodic motion and simple harmonic motion. In every periodic motion, we don't have restoring force. For example, Earth is revolving around the sun. It's periodic motion, but it's not simple harmonic because there is no restoring force. But mass spring system in here, there is always a force acting on this mass, always pulls this mass back to unstretched position. There is a restoring force. That's why vibration of this mass spring system is simple harmonic motion. One more thing. The position of the object when the spring is unstretched or uncompressed is called equilibrium position. Why is it called equilibrium position? If you don't compress or stretch a spring, which means elastic force is zero. Yani net force acting on the object is zero. If net force on the object is zero, what does it mean? Object is in equilibrium. Equilibrium condition it is. That's why this unstretched position from now on will be named as equilibrium position. Yeah, equilibrium position is the position at which net force acting on this vibrating object will be equal to zero. Okay, questions?
Teacher, can you explain simple harmonic motion again, please?
Yeah, it's a periodic motion. Yeah, simple harmonic motion is for example, this vibrating mass system is simple harmonic motion. So there it must be periodic, yes. But this periodic motion must be caused by some restoring force. What does restoring force mean? A force acting on the object must always pull the object back to its original position. This is original position, unstretched position. This force is always pulling the object back to that original unstretched position. That's why we say that this is simple harmonic motion. Page 11, conceptual challenge 1. This is this question is defining the difference between the periodic motion and simple harmonic motion. Question is asking you that the motion of the Earth orbiting the sun is periodic. We know it's periodic, it's repeated motion. So Earth is initially in here. Later it moves, comes to the same point again, and again. So this is periodic. Is this motion simple harmonic? Why or why not? So this is not simple harmonic because the force acting on the Earth is towards the center. And in this simple harmonic motion, if you look at this figure, you are going to see that restoring force is always along the direction of the motion. Yani object is moving in horizontal, vibrating horizontal. Restoring force is also in horizontal. If the mass was vibrating vertical, you would observe that restoring force is in vertical. Yani elastic force or restoring force always becomes parallel to the direction of the vibration. And restoring force always parallel to direction of vibration. But in this question, direction of motion is tangent to the circle. But centripetal, this force, gravitational force, is perpendicular to the direction of the motion. Any force perpendicular to the direction of the motion is not restoring force. It is centripetal force. That's why we have centripetal force, but we don't have in here restoring force. If there is no restoring force, then we cannot say this motion is simple harmonic. This motion is not simple harmonic because there is no restoring force acting on this object.